So welcome to today's lecture on LTE. Today I'd like to talk about two of the key enabling technologies. The first one is Mimo technology, and then next we'll spend most of today talking about OFDM. So to begin with, MIMO stands for multi-input, multi-output, and really what it's referring to is the fact that there are multiple antennas used at both the transmitter and the receiver. So MIMO is fully integrated into the LTE standard, and it has a couple different modes, different ways to use MIMO. So the key different ways to use MIMO, first of all, is for diversity. And we talked about diversity earlier in the semester, and remember what diversity is about: having different paths, multiple paths to your receiver. So with MIMO, the way the diversity is used is you have multiple transmit antennas, and each one of these transmit antennas has a different path to the receiver. And so by taking advantage of these different paths to the receiver, you have diversity. Okay? And so the key here is that if one of the paths is bad, then perhaps the other one is good. You're really sending the same information over both paths. So you really only need to get one of them through. And so you would want to use diversity in situations when the channel is poor. If you have bad channel conditions, then diversity will really help, because if you have one bad path from one of the transmit antennas, then hopefully due to the vagaries of fading, the other path will be good. And so in order to have a bad signal, basically both of the signal components would have to be bad, and hopefully that would occur with low probability. So the other key mode is spatial multiplexing. And there's actually two different flavors of spatial multiplexing. And the key idea here with spatial multiplexing is, instead of sending the same information over both antennas in order to get diversity, you actually send different information. You can send two layers of information. Okay, so now there's two layers. They could be as simple as sending one signal from one antenna and another signal from the other antenna. So these like two information-bearing signals that are simultaneously being transmitted over the two antennas. Or in some cases, slightly more complicated signal processing might be used so that some combination of the two informations are being sent over the two antennas. But no matter how you do it, what happens is, by using spatial multiplexing, you're getting two layers, two information-bearing signals out at the same time. Now, what can you do with that? Well, on the one hand, you could do what's called multi-user MIMO. So you have two signals. You could send one of those layers to one user and then the other layer to the other user. And even though either one of these users is not experiencing a better data rate, together you're able to have more throughput in your cell, because you're able to send two signals at the same time using the exact same time frequency resources to two different users. Okay, now the other way you could use MIMO is single user MIMO. And the idea behind single user MIMO is, well, you send both of the signals to the same user. Okay, so here we have two layers, a red one and a blue one, and they're both simultaneously being sent to a given users. Now, one caveat here, if you have two transmit antennas, in order to do single user MIMO, you also have to have two receive antennas. And you can kind of see that here. This laptop is showing 1, 2 antennas. But the benefit here is you can double your data rate to this one user. However, in order to do this, you do need to have good channel conditions. You no longer have a diversity effect, so both of these signals need to get through in order for you to enjoy that doubling of data rate. If only one of them gets through, well, then you're missing the other signal component completely. So in trying to decide when to use the diversity mode versus when to use multiplexing mode, well, you want to use diversity mode when the channel conditions are poor, and then diversity gives you multiple ways, multiple opportunities to get the signal to the receiver. On the other hand, if you have a good channel, then use the multiplexing mode, because with the multiplexing mode now, you can take advantage of that good channel and actually use that as a way to increase the data rate. You could, in theory, double the data rate by sending two different layers from the two antennas. So the other key enabling technology that I wanted to talk about today is OFDM, or orthogonal frequency division multiplexing. And so the idea with orthogonal frequency division multiplexing is to take the overall signal, and instead of transmitting a wide bandwidth signal, it instead breaks it up into a whole bunch of small narrowband signals. And in LTE, each signal is 15 kilohertz in width. And these signals are packed very closely together. In fact, they're 15 kilohertz apart. And so you can pack in a whole bunch of subcarriers. And there's a lot of benefits to using OFDM, as you'll see shortly. But the key benefit comes in terms of scheduling. So now the idea here is, in this example, our base station is transmitting, let's say, M frequencies over a given time. This one time interval is what's called an OFDM symbol. And then in the next time interval, it'll send another set of M frequencies, and it does this repeatedly. So each time instance, it sends a OFDM symbol, and an OFDM symbol is actually a separate signal being sent over each one of these M frequencies. And each one of those frequencies could carry, let's say, a QAM symbol or a QPSK symbol, and these could all be transmitted in parallel. So in LTE, you have this time frequency grid, and here you can see frequency is the vertical axis, and time is the horizontal axis. And so what you have is you have frequency bins, and those are 15 kilohertz in duration. And then you have time, and you will see the time is less than a millisecond, typically 1/12 or 1/14 of a millisecond. And the intersection of a time and a frequency is what's called a resource element, RE. So resource element is really the fundamental component here used by LTE. It's a fundamental component of scheduling, and you'll see that as I go through a little bit more detail on scheduling. So now the resource elements are grouped into blocks. They're called resource blocks. So here I'm showing one resource block. It's in yellow. And what is a resource block? Well, a resource block has 12 frequencies. Why 12? Well, this is just a decision of the LTE Standards Committee, the 3GPP committees that came up with it, thought that this was a good idea. And we'll talk a little bit more about the significance of having 12 frequencies in a resource block, but it's 12 subcarriers. Okay, and then in time it's 1 millisecond, as you can see on the figure. So using OFDM allows LTE to do what's called channel-dependent scheduling. And this is all based on the idea that at a given time, different frequencies are better for some users than for other users. And so what we have here in this diagram up at the top, we're looking at the channel conditions at two different users. And so we got user 1, and user 1 is being shown in gold, and user 2 is being shown in blue. And you've got time going along one direction and frequency going along the other direction. You can see some time frequency instances, gold is better, user 1's better. Out here, gold's better. But then other places, blue is better, user 2's better. You can see different spots here where user 2 is going to be better. So what LTE does is it tries to schedule resource blocks at each given time instance to whichever user has the better channel conditions. And you can see that in the diagram here. Generally, where the user 1 is better, in the lower diagram, you're getting gold. These are the actual resource blocks that are being scheduled. And the gold resource blocks are being scheduled to user 1. Why? Well, because user 1 is better in those frequencies. Meanwhile, the blue blocks are showing you what's being scheduled or sent to user 2. And those are frequencies for which user 2 is better. So that's the idea of channel-dependent scheduling, and it's basically predicated on trying to maximize the satisfaction of the users by using the best frequencies to reach them. So this slide kind of repeats what was being shown on the previous slide, which is just that at any given subframe, 1 millisecond increment, the scheduler at the base station can transmit any number of resource blocks to the users in the cell, and it always tries to use the best frequencies for a given user. So in the first subframe here, perhaps you got user 1 is being sent resource block number 49, user 2 is given resource block 50, and user 3 is given resource block 1. You can schedule multiple resource blocks to a given user, so their bandwidth could vary. So you can see in the second time interval, perhaps user 2 is being given a whole bunch of frequencies, while user 3 is given just one, and maybe user 1 doesn't get any at all. So you get this variable bandwidth kind of behavior, and the minimum amount of bandwidth that a given user can get at any instance of time is 1 resource block. 1 resource block, remember, is 12 subcarriers. So another benefit of using OFDM is that it allows for a variable amount of spectrum to be used in a given cell. So LTE is not a one-size-fits-all solution. In fact, there are 6 different bandwidths that can be used within a given cell. So this will be the amount of frequency available to use to schedule within a given cell, and it could be as low as 1.4 megahertz. Now, 1.4 megahertz corresponds to just 6 resource blocks. On the other hand, the maximum size is 20 megahertz. In 20 megahertz, you have 100 resource blocks. The example I showed you on the previous slide, well, here there were 50. There are 50 here frequencies available for scheduling, so that would correspond to a 10 megahertz system bandwidth. So this kind of gives you some ideas what the maximum amount of bandwidth you have available. If you have if you're operating with the largest carrier bandwidth of 20 megahertz, then you have available 100 resource blocks. 100 resource blocks, of course, corresponds to 1,200 subcarriers. So basically, you can schedule anywhere from, on the low end, 12 subcarriers, that's 1 resource block, all the way up to whatever the maximum number of blocks that can be supported in your cell. And here, the largest cell bandwidth is 100 resource blocks, so that would be 1,200 subcarriers. So another benefit of OFDM is it allows for really very simple signal processing in both the transmitter and the receiver. And so these diagrams here kind of give you an idea of what's involved. Now, we want to think of the symbols that are being transmitted here depicted by A0 through AN-1. Those we want to think of as being in the frequency domain, but in reality, what we need to transmit is, in fact, a time domain signal. So we need to convert from the frequency domain to the time domain. How do you do that? You use an inverse Fourier transform. In digital hardware, you implement a inverse Fourier transform, of course, as an inverse FFT operation, FFT being a fast Fourier transform. So once it's in the time domain, it can be converted from digital to analog. Signal X of t is transmitted over the channel. And then you got your receive signal, R of t comes in. And basically, you just have to reverse the process. So you'll need to convert now from the time domain to the frequency domain. That's achieved by using a FFT algorithm. Okay. The equalization is, of course, compensating for the frequency selective effects of the channel, and equalization can be done very easily in the frequency domain when you use OFDM. Now, OFDM does require what's called a cyclic prefix, and the idea of a cyclic prefix is it creates a small amount of guard time from one symbol to the next. You can think of this as being a guard time that gives enough time for the signal energy to catch up, and this is particularly important in a so-called time dispersive channel. So most wireless channels are characterized as being time dispersive, and really all that means is that when you stick the signal into the channel, it has a certain impulse response that tends to have some parts of the signal arrive a little bit later than other parts. It kind of smears the channel out in time. And so the cyclic prefix is needed in order to create some isolation from one OFDM symbol to the next. And so you've got a small guard period from one symbol to the next, and it's called a cyclic prefix because the way it's generated is you take the signal and then you take the very end part of the signal right here and you actually copy it and you bring it around to the front. So it's a cyclic prefix, and the cyclic prefix just assures that the end of the signal is the same as the beginning of the signal. Okay. The reasons for doing it are a little bit more subtle, and they get into the nuances between circular convolution and the FFT. But the length of the cyclic prefix depends on how dispersive the channel is. So in LTE, there's actually two different lengths, a normal and an extended cyclic prefix. So when would you use one versus the other? Well, it's based on how dispersive the channel is. You would use the normal, which is the shorter one, when the channel is not very dispersive. When would it not be dispersive? That would tend to be maybe in an indoor use or maybe a small cell, so most of the signal arrives at the same time. It's not very dispersive. So you'd use normal in a non-dispersive small cell setting. But then the extended cyclic prefix, it's a longer cyclic prefix. It's used in a more dispersive environment. When do you have more dispersive environments? Well, this is when you're outdoors, you have larger cells, you're vulnerable to very long reflections, and so signals could be arriving at paths that are very different in length and therefore come at different times, and so you have a lot of dispersion. But LTE allows for both of these options. So OFDM has a problem though. And the problem is that it increases the so-called peak to average power ratio. So what is peak to average power ratio, or PAPR? Well, it's just the ratio of the maximum power divided by the average power. And I have an example at the bottom written in MATLAB, but basically what it's showing is that when you take a signal and you pass it through an IFFT, it increases the PAPR. Well, why does that matter? Well, if you're using an RF power amplifier, then the PAPR tells you how far off you need to back off with the amplifier, and so systems that have a large PAPR typically have to use a more powerful or a more expensive power amplifier, and the battery tends to be not as efficient. So knowing this, LTE has a different transmission scheme on the uplink. Strictly speaking, the uplink signal in LTE is not OFDM, but it's a derivative of OFDM called DFT precoded or DFT spread OFDM, or sometimes just more commonly called single carrier FDMA. And so single carrier FDMA, it looks a lot like what we saw for OFDM. In fact, you have an inverse FFT right there. You add a cyclic prefix. But now what you do is before you go in through that inverse FFT, you first pass it through a forward Fourier transform, or a DFT. And it sounds a little counterintuitive because the DFT is counteracting what the FFT does, but that's actually good because that removes the PAPR increasing effects of passing through the IFFT. Okay, so, but you can still use, for instance, you can use a frequency domain equalizer here. Most of the signal processing is identical to what you had with OFDM, but you have the additional benefits of the PAPR being more beneficial than if you were to just use OFDM. Okay. So finally, there's another detail I wanted to share with you, and that's this idea of transmit timing advance. And with an OFDM or an SCFDMA uplink transmission, you got to make sure that the signals all arrive at the base station with the same relative time offset. So if you have two terminals that are transmitting in a cell at the same time, you better make sure that their signals arrive at the same time at the base station, or else their transmissions won't be orthogonal, and hence they'll interfere with one another. So what LTE does is it actually will time the transmission so that the more distant UEs, more distant terminals will actually transmit a little bit earlier than the closer UEs. And so by doing that, they arrive at the same time. And so in this example, you have a terminal 1 that's transmitting on the uplink and a terminal 2 that's transmitting on the uplink, and they time themselves in such a way that they arrive, you can see here, at the same time at the base station. So that's all I had for this particular lecture. Please look for the next one, and thank you for your attention.